Yeah, it is. You are the confident, right? Yeah, we exchange. I don't know, but no, not the lot of yeah, because we have some. Astronomical.
Ayakta kalmak. Evet.
Evet. Tamam iyi oldu. Öyle yaparsın. Zaten bu sene peki bir Paolo sen şu Antonio yaşıyorsun. Ben başlasam Samsun için şeyler Hazır mıyız? Hayır, hazır mısın? Hadi sesler. Tamam. Welcome everyone, both online and offline. We are honored to be hosting Paolo Molaro today here at Istanbul University and Department of Space Sciences. Let me quickly introduce him. Paolo finished his undergraduate studies at the University of Trieste in the physics department. He did his PhD in CISA, again in Italy, on the determination of the abundance of lithium abundance. Lithium, beryllium, and boron. And then since 1987, I guess you've been working at the University of Trieste. He was the director of the observatory between 2000 and 2003. And his research interests include primarily nuclear synthesis, light element abundances on extremely metal poor stars, and many others. He'll be around, so if you want, you can just catch up with the questions and so on. So welcome, Paolo. Thank you very much.
How can I move the slides? Just prepare this. Okay, thank you very much, everybody. I'm very pleased to be here. This is my second time. The reason because I'm here because I'm attending a Galilean week at the Galileo Galilei High School here in Istanbul. They organize every year. So they called me to give some lessons to the students. And this year I did somewhat around the nova that exploded in the sky in 1604, which was very important at the time because Galileo gave lessons on, was the first, let's say, broken the idea that the sky was perfect, eternal, like Aristotle or the and Galileo wrote a book about that, which is on the nova star, written by Exodon, because it's not written by him, by Cecco de Ronchitti de Bruxelles. Okay, but we don't know, but we certainly it's him because and it's written in dialect, in Paolo dialect. Okay? So Galileo tried to confuse again, not to be, attacked by the church and so on. But that is the first book that we have formally against the Ptolemaic and Copernican model. So that's very interesting that I did here. And I invite you to keep contact with the school. And if you want to give lessons during this week, Galilean weeks on astronomical topics, in Turkish, you can do in Turkish. I do in Italian, but they first talk is Turkish. So you are very welcome to keep contact with them. Okay, I have a lot of ties with Istanbul, and I think that when I was doing my doctorate, that was by Margherita. There were a lot of people from here coming and visiting the observatory. So I was going, a lot of Turkish people around. And I remember, I don't really know them personally, but these are the names that I try to remember. That of course are all the pilot now. Okay. But okay. So sorry. Yeah, there is okay. Okay. So a second contact is actually with Raimondo Daronco that I discovered is very important architect here, and he did all these things in here in Istanbul, including I think the old observatory somewhere must be here, I think that this one, that's the one we're talking. And this is very famous here, more famous here than in Italy. And actually, he's born in Gemona, which is a very small village close to the another small village where I have been born. So that's it. And actually, my house in Udine is in the Ronco Street. So that's all. But another fact is that one of my best collaborators, actually my tutor when I did my thesis, and now collaborator, is Salvelli de Luigi. Okay, and grandfather or his grandfather is here, is Italo Salvelli, but Robert was a musician of the court of Sultan Muhammad V. And he wrote the march for the Sultan, which is, I think, the note here. Okay, so let's come to the science at the end. Okay, the subject of today is the astronomical origin of lithium. And I think to say these are the collaborators, and here you have the research. Okay, So that's what I'm going to present is also not only what the contribution of that. Well, lithium is one of the most studied elements. Okay, it's at the crossroads of several things in astronomy, from stellar structure. You know that lithium is depleted by unknown reasons in the sun, and we have the lithium in the warm stars, and so on, the stellar evolution. So it's linked to the primordial nucleosynthesis, to the Big Bang cosmology, and so on. Despite of that, and is actually his origin, astronomical origin, is unknown, as I will say, understanding. And there are two major, in my view, I'm biased in this way, but in this way, what I'm saying, but there are two main issues with lithium. One is astronomical origin, and the second is what is the precise lithium value coming from the Big Bang, from a primordial. So I address these two points in my talk. Okay, about the origin. You see that this table, astronomical table of elements that appear since a few years, that are shown in all conferences and so on. If you go in the detail and you see what is the lithium origin, you see that in this case, for instance, there is a Big Bang, emerging neutrons, not so. If you read down, it must be the cosmic rays, and you will see that. But then there is a yellow, is dying low mass stars, which I don't know actually what we see. Dying low mass stars, for me, does not mean anything. Or for instance, if you go here, you have a fusion star. Sorry, the red one, yes, is fusion stars, which again does not make any sense. But if you go here, you can see just the cosmic rays. But let's say that it's completely a mess. And the reason is because we don't know actually where the lithium comes from. What is the reason exactly? And the third paper, we have to go back to the Hoyle Fowler Displacement paper, okay, where is a Bible of chemical evolution of origin. And they discovered, they established the fact that lithium is destroyed inside stars at the temperature of 2 million degrees. And but since already at that time, lithium was measured with meteorites at this level, okay? I use this notation, which is log of lithium over age plus 12, okay, if you're not familiar. Anyway, lithium was in meteorites, but destroyed in the star. So they asked where the lithium comes from, okay? And they couldn't find the magnets in this paper, and they told the X process. Okay, we have given a name of this process collectively to the mechanism makes it decide the lithium, beryllium, and boron. Some discussion of problems in this section. So they call it the X, let's say, unknown process. But certainly they say the process to be non-term, so I have not for the inside stuff. Okay. Oh, let me go on. So, okay, after that paper come evidence that lithium is produced primordially. Okay, and we know today that thanks to the CMB baryonic acoustic oscillations that provide the value for the baryon densities at the nucleosynthesis time, we can predict precisely what is the outcome of lithium primordially. Okay, and also supported by the deuterium, which is in the ionization equation of the Okay, so if you take the primordial value, you get out this unit 0.75. Okay, so we know exactly what it is that. Then another established lithium mechanism is the cosmic rays. It's nocturnal. It was already in the Fowler Barnage oil paper. Okay, but was finally done in this paper by Real Solar Barnage 70. They established that actually is the cosmic rays that hits and breaks the nuclei in the stellar medium, and so you have a product, a byproduct. You have a light dynamics human body. Okay, but we can control how much lithium is done this way. And we can do it because of beryllium. Beryllium is, this is the only mechanism you can do beryllium. So, you know, just in relation to the cross section, you can estimate how much from the beryllium abundances, you can estimate how much lithium abundances you have, and you can end up with this value. Okay? So, if you put all together, and okay, there is a nice number that has come out from lithium. If you take the lithium in the meteorites, which is measured in the solar system, and you assume that it's general in the galaxy, okay? You put the elasticity mass. So you take the abundance of lithium in mass in meteorites, you multiply for the mass of the galaxy of hydrogen, not everyone, of hydrogen, so you have to multiply over 7. You get out about a very nice number. It is 1,000 masses of lithium in the galaxy. Okay? Well, if you take the percentage of each of this, spallation can produce 10%, but good nuclear synthesis, we will see that most 25%. But also you have to subtract the fraction of lithium that has been destroyed inside stuff. So it's about 10%. So the rest is 75%. Okay? So 70% which is not accounted by any established astronomical source. And what are the possibilities of what is suggested that this is being done? Some HGB show lithium evidence, okay? But these are only on the massive HGB of this mass. And if you put that in a chemical evolution model, you find that actually they are too few to make a significant fraction of the lithium. And you have just a few percent of the 1,000, okay? So massive. So that's rule out. Another idea that came out over the years is that lithium is produced by cosmic breaking by neutrino spallation. When the supernova explodes, you have neutrino production that can break oxygen and other atoms out in the outskirts of the explosion. But this does not work because if you have a supernova actually making lithium, you have a very quick rise in the chemical, in the storage of lithium, in the chemical evolution of lithium abundance in the galaxy. Okay, and then there are also issues with the role that has produced in the same level. So also this is not. Then red giants probably is the low mass dying stars that was in the table before that we have seen. There are a few percentage of giants, the giants that show lithium. Okay, but there is a very small fraction of lithium that produce more than what we see in the meteorites. But in order to enrich the interstellar lithium, you have to have much higher levels. Okay? So that's then with this values you cannot really make the lithium. Okay? This has been favored model by Romano and also others, but actually they took extreme assumptions in the chemical evolution in order to get significant amount of lithium out of that. Then in the late 70s, Sumner started et al. They made the hypothesis that nodes then make the lithium. Okay? There was the giants that was proposed the polar mechanism in order to make the lithium in the giants, and they say, well, maybe also in the nova is happening the same. And actually, in the nova, you can have a temperature of this sort when there is a thermonuclear reaction going on, and you can have a beryllium 7 reaction, okay, with this reaction, helium-3 plus another. And with this reaction, beryllium, it can be also destroyed by the same temperature, but if it is taken out in a cooler region by the Fowler mechanism, by convection, this is the Fowler kind of mechanism working for the giants. And if it is taken out from the hot region, you can have that beryllium 7 can survive. Okay, and since beryllium 7 is unstable, and the decays with meaning half-life of 23 days actually end up with lithium. That was the proposal, okay, making the late 70s. But astronomers, several astronomers, looked for the lithium line in the explosion, the overexplosion of the outburst spectra, okay? And then we find for decades, including me, and these are some of the papers, but more, you know, the astronomy, when you search on something that you don't find, you don't publish, okay? So me too, including me, I looked for lithium in the outburst of nova, didn't find it, didn't publish, okay? The first change came in 2015, Luca Izzo et al. They found a line which it was consistent with lithium. So that we are totally looking up here, but this is the lithium line displayed, okay, at the velocity of -5 outward velocity, the standard velocity of -560 per second. There is a lithium line. That's it. First and so far unique detection of lithium line in okay. But what's important, okay, the year later, some Japanese group, Tajitsu et al., and myself in 2015, we looked for the presence of beryllium-7. So beryllium-7 is the father of beryllium-7, okay? And this, what should convince you, this is the spectrum that I got from the Nova Sagittari 2015. And here is the velocity on the bottom. Here you have the black is the beryllium line, the beryllium region, okay? And all the metals that are seen, you see calcium, iron, and this is the hydrogen, are plotted on the same velocity scale, okay? So you can see that you have when the explosion, you have a nova explosion, you have some components in absorption, okay? And so you see that absorption is on all the metals, okay, including the beryllium region, okay? But what's make the identification sure is that beryllium is a doublet, okay? So you have a doublet which are separated by one Armstrong, so, okay? So when you see the line for the metals, calcium, iron, and hydrogen, you see that you put only one line of beryllium, you see the other component, okay? So this is a smoking gun that actually this line is beryllium-7, right? And the precision is, this is the UV spectra that I got, and the precision is at the level of kilometer per second. So you can actually distinguish beryllium-7 from the isotope beryllium-9, which is a stable one, or beryllium-10, or the other one, okay? And so this is detection of beryllium-7. And this is the only place where you can see beryllium-7 in the universe, as you produce here on the Earth, because it decays, okay? It decays in 53 days, so it's unstable. Okay? And this proves that actually the idea put forward by Starfield and collaborators in the late 70s is the right one. It's a good one. Okay? Good work. And confused. So this was a slow nova. Okay, the slow nova means that there is a big ejecta and then lasts long. Okay, so we follow this nova, okay, in the months, okay, and we were expecting to see. Okay, but the first thing is, sorry, I forgot to mention, go back the line. So we can prove that these lines are the beryllium-7. But what this? Okay, this huge absorption. Is this beryllium-7 as well? Well, who knows? You know, you have a lot of flags there and so on. But what happened here, and you see that there is also corresponding a similar absorption profile in the other species, elemental species. So we followed actually the nova, because it was a slow nova, Okay, and we, at the end of the day, 82, so after 3 months, actually, we saw that the line becomes optically thin, and so it reveals the components, okay, inside. And the components show the double structure of the beryllium 7, which means that all this huge absorption was beryllium 7. Okay, and that's it, makes this second after hydrogen. Beryllium 7 is the one that produces more absorption in the spectrum, is dominating the spectrum. And since we fall, we were questioning, what about lithium? We were expecting to see lithium. Because we say beryllium 7 after 53 days, it decays in lithium. And actually, we couldn't observe. This was a puzzle. You see the lithium line. At day 58, we should find, if all that was beryllium, here we should have a huge line of lithium. Okay? So we came up with an explanation of that, that explains also why all the astronomers actually failed to detect, to observe lithium 7 along. And the reason is because the decay of beryllium 7 into lithium 7 happens with the capture, electronic capture, okay? But if electronic capture is from the internal K shell of the atom, actually, from beryllium 7, you decay and you have lithium 7 ionized. And lithium 7 ionized has no optical, lines in the optical. So there is no way to see if the lithium is all ionized in the outburst of the nova. Okay? And so this is our explanation for why the astronomers fail to detect lithium along the years. Okay? And this means that you have a huge outburst of lithium, beryllium 7 and lithium, ionized lithium, which is completely unabsorbable as a lithium when from optical observation. It relies on the X lines, so in X regime, and they are very difficult to detect. So, since then, we started to follow the bright nova. The observations are very challenging because the observing lines after 3,130 Armstrong is very difficult at high resolution. There are few instruments in the world that can do Google, some DFT, Subaru, and I don't know, some others. I don't think that it's only these two spectrograph actually. And so along the years, this means that the nova has to be bright. Okay, we are following. We had a target opportunity approved time to time from ISO. You know, it is so all this is so difficult. But anyway, we have more or less observed all the nova brighter than 9 magnitude since then. Okay, and today this is every nova is the one different from one of the other. I don't want to show all of that. I want that this a very clear case is a nova Ludwig 2017. Only one observation, and you can see that the correspondence of absorption here of sodium and calcium. Here you see the double, which is the smoking gun of the beryllium cell. Okay, these are very simple structure, very high velocity. Here are about -2,200. So the nova is very quick, fast nova, and then it disappears very quick. Okay, but that's beryllium as well as there. So we want to go, this is I just want to show it's interesting case. Give me a warning sometimes. Okay. We went to that pioneer carbon actually, because the island was covering the range, and we surveyed it, to show also this for this reason. This is nova is 1991. Okay. And you can see here the magnesium line absorption, and here is the beryllium absorption. Okay, so actually that discovery could have been done much before. Okay, that's I wanted to show that, and I want to show that also because this is compared to magnesium, which is another element. Because we will see now we have to find the abundance of So that's the next problem. We also protect beryllium as clear evidence that we should know that in the small Atlantic cloud, okay? And I don't want to go into this detail because, okay, but this means that beryllium-7 is made also in the low metallicity because the metallic clouds are the lower metallicity, which also help because you have less bands here in the spectrum, but that's is also, and the hills are different, I will explain in a minute. Then we also detect beryllium-7 in the RS50, is a recurrent nova, is composed by a red giant with this period and so on, and it exploded in August 2021. And we made observations 2 days after the explosion, and we think we'll find beryllium-7 here. This different is just the ring of a giant before the explosion, so you don't have to put that. But you have this correspondence between the absorption of the metals and the beryllium, which tells you that also collected nova can make beryllium-7 with the same mechanism of the classical nova. So the problem is next, what is the abundance? Okay, what is can be produced by this nova? And by using the small value, when you are lucky, then you have these small components which are weak, and so they are also unsaturated. Okay, you can get a very good equivalent width. Okay, so you can measure since it is beryllium is a resonance line, you can measure the abundance compared to calcium lines. Okay, so the abundance is very well regulated. Okay, because if you assume that all the calcium 2 and beryllium 2 ionized are in the same dominant stage of ionization. Okay, so then when you assume the calcium abundance, you have to assume the calcium abundance, you can compute the beryllium abundance we refer to calcium. Okay, so we did that, and this is the collection of all the measurements that we have done so far. So we have 8 classical CO nova, 3 oxygen neon nova, 2 nova in the small dynamic cloud, 1 regular. Okay, and this is the beryllium abundance in the scale that I was mentioning before, plus cloud. Okay, and which beryllium, which is the same as lithium. Okay, so if you take this average here, you forget the up and down now, but of course, this means that we have found beryllium-7 in all the nodes that we found. There is only one uncertain case, but is ubiquitous. So we have also always observed beryllium-7. So the abundance here, the average abundance here is 7.4. Okay. I want to remind you that metallitic is 3.3. So we are here 4 orders of magnitudes higher than metallitic test. Okay. And okay, but there is a problem. There is a problem that the NOVA models actually cannot explain such a high beryllium-7 protection in the node. So far, the models are in this range. Okay, so there is a tension between the abundances as we observers measure in the outputs of the NOVA and what the theoretical people that working on NOVA can produce, let's say, with so we have this this problem now. I know that they are trying to revise the models. Okay, but so far it's like, okay. So next point is, are these nova significant production? Can they be the explanation for the astronomical origin of lithium? Okay, we need another input, that is the nova ejecta, because one thing is the yield, how much beryllium compared to calcium, but then we have to multiply by the mass of the jet, okay, which is another unknown. The mass of an ejecta could be varied. The nova people, the experts say, between 10 to minus 4, 10 to minus 5, okay? So let's take 10 to minus 5, which is a smaller ejecta. And if you take this 10 to minus 5, and you multiply by the hills that have been derived in the outputs, you get this number, which is 1.4 10 to minus 9 masses in lithium per event. Okay, well, you know what. Okay, so you can do now, you multiply the lithium produced in one nova explosion by the nova rate, the number of nova that you have every year in the galaxy, times the time of the galaxy, and you get about 420 masses of lithium, okay? Which is very close to the value that we need, okay? And this, just only this computation tell you that the nova actually are very important, to be an important lithium source in the galaxy. But we can do better than that, of course. We can do a normal classical chemical evolution model. And so the state of the art, we did a chemical evolution model for lithium as the other people did, but with a difference. Okay? We took the state of the art models, but instead of using all the ingredients in order to make the lithium production, we took the nova yield as a pre-parameter. Okay, so we forced we included the known sources, so VDN, galactic cosmic rays, HB, okay? But the nova, we kept it as the yield as an unknown pre-parameter. And we wanted to match the chemical rise of lithium. This is the lithium, the points here are the lithium measured lithium in the stars, okay? And so here you have metallicity, okay? So this is the halo. You start from the primordial value, then you get up and you start to have lithium production here, okay? Then in the stars, lithium can be also destroyed, so you have all this scatter, which you don't have here in the halo, okay? So in order to, what the chemical evolution models for lithium, I have to explain this rise here, okay? And if you do this with this model, you see that, for instance, this is, if you have no production and you have only expression, the lithium abundance go down here, okay? Then if you have the HB, you see the HB does not contribute at all, you have just all this increase here. Then you have the cosmic rays, and you get this, which is 10% more, okay? This is very unknown, but if you want to fill this with the nova, you get that, okay? This is by model, by construction. But the interesting thing is that if you know that to do that, you have to make about 2 10 to minus 9 lithium nova per event, which is exactly what we measure as an average in our measurements in the albums of everything. So this, from my view, tells you that the nova can do the work, okay? So there is, as I say, this problem with the models, okay? And in principle, there is only one way, but in the future, I mean, there is only one way, I don't want to say that, there are many ways, but certainly one way to solve that, or that we possibly in the next years, is to detect the gamma rays due to the lithium decay. When the beryllium-7 decays into lithium, you have an emission, the gamma ray emission of 478 TeV, okay, which is this one. And this line has never been detected so far in the gamma stratum, okay? It's a very classical reaction, but the line has not been detected because the nova probably are too far away. In the nova Sagittarius 2015, we got actually serendipitous integral observation in X-ray. We analyze the data, and the data didn't show the line, okay, but are consistent with the distance, okay. So actually, what we need is a nova close by, okay, and maybe this line is the thing, okay. So we don't, we need a nova closer than 500 PC parts, just to be sure. And then this problem will be solved unless the theoretical people will be nova can explain, can produce more beryllium 7, or someone can explain that our method to derive the boundnesses is wrong. If we are wrong by one order of magnitude, okay, then the tension between the models is solved, but you still have to explain where the lithium comes from. So, putting things another way, if a theoretical people is right, we still have to find the origin of lithium. Okay, it's the only element where we don't know comes from. Okay. And I think that we have an integral target opportunity program going on in integral that unfortunately is ending a slide this year. But possibly we have results for the next month. So stay tuned on that. I cannot say any more. How much time I have to go?
You have all the time, no problem. It's just 40 minutes or 38 minutes.
Okay, good. So I go for the next second topic. Related to, I don't know if there are questions interrupting me on this. Okay, the second, I would say, the second big problem that we have with lithium is exactly the primordial value. Okay, how much comes out for the Big Bang? You see that, okay, these are the outputs, the model outputs. This is helium, deuterium, helium-3, and lithium from the Big Bang. Okay, the 3 minutes. This is as a function of the value to photon ratio, which is the main and only parameter working in the Big Bang. As we know now, this is for 3 neutrino families, and also the neutron lifetime is now 1 to 2. So actually, the thickness of the lines here is due to the error in cross sections of the main reactions in the Big Bang, and in the yellow there are observations. Okay, so. This is, of course, helium is very sensitive to the speed up of the universe, so it's very sensitive to the neutrino species, but here it is a fixed, because I'm free experiments, okay? So these are in the yellow, there are observations for the little part of the helium, but the helium probably you don't see, but this line here, the helium now is very, very well determined. Okay, is a measure of the few percent, which is amazing, really. And if you have this value here, so you get this value to the ratio of the value to total ratio here. Okay, and in blue here is the value corresponding value that comes out from the power spectrum of the peaks in the CMB. It gives out also the value of density in another vector that they coincide. And if you take this value here, you get this expectation. This is the lithium curve because of the several reactions. There are destruction, production, and so on for lithium. So you get this value, which is 2.7. Okay, here. Why? The observations are here. The observations of lithium abundance in the halo stars differ by a factor of 3 compared to the expectation of the thermal organization. Okay, this is these are the points. These are the observations. Okay, Okay, these are different authors, and in this scale it's 2.2. Then this is the value which you expect for the Big Bang. We see that there is this desert here where there are no observations. Okay, so that's difficult to explain. This difference is by a factor of 3. There is something going around here. I mean, the thickness of the plateau is considered an important fact, but here it seems to be something wrong going on. Okay, at the lower degrees. So this is where we are, and we also, you know, that one of the major results of the Gaia satellite is the discovery of merging bodies, the galaxies that merge in the halo, like Enceladus. Enceladus is a body with a mass estimated of the Magellanic Cloud, okay, that collide with the Milky Way, something like 10 gigayears ago, okay? It's possible responsible of thick disks and so on. So if you isolate these stars kinematically and chemically, actually you can see what is the lithium in these stars that are created because they form in different galaxies. And we did this a few years ago, and actually we found that the lithium in the Enceladus candidates stars is the same as those in our field. Okay, so let's say this is been also confirmed by the Gala people, by Simpson et al. Okay, they also find some odd stuff here, but anyway, most of the bulk of the stars are on the same region that the heliostars in the galaxy, showing that if there is a sort of lithium problem, cosmological lithium problem, this holds also for other galaxies. Okay, this is really important because observing lithium in another galaxy is very, very complicated. Probably the challenge of the next big telescopes and that generation. So, I mean, how do we traditionally? I mean, nuclear people try to fix that, looking at the cross sections and so on in the primordial nucleosynthesis, but apparently there is no way to fix the problem that way. Okay, so the most everyone today is more or less convinced that is a stellar problem, and they try to the stellar problem because there is a meltdown in the lithium abundances at low metallicity, so the lithium plateau, so-called free plateau, is at 60 year time to go down, and also recently there is been a withdrawal of the presence of lithium-6 in the halo star. Okay, for a few years, Astronomical, the Australian group, claimed that there is lithium-6 in the halo star. Okay, now it's gone. The importance is since lithium-6 is more fragile, if it is present, if lithium-6 is present, lithium-7 cannot be destroyed. Okay, let's put it this way. Okay, because lithium-6 is more fragile. Now lithium-6 is not anymore present. Okay, especially this paper, I think, put an end of these claims. So stellar depletion by lithium-7 is possible. Okay, and there is actually claim by, for instance, fields and on. Okay, there was an important. Okay, let me just before that. But you can have a stellar fix because lithium can be sink down in the stars because of gravitational setting, for instance, and then destroyed. Okay. However, the fix is not so clear because you certainly have diffusion, but if you have diffusion, you have the diffusion is very sensitive to the mass of the star. Okay, so if you go up with the temperature here, you have stars with a greater and greater mass. Okay, and so the diffusion goes in this way. So you have an increase of diffusion with the more massive stars. Okay, so wide observations are flat this is a speed problem. Okay, so you have to have the two mechanisms, diffusion, and then you have turbulence in order to stop the diffusion when you have a higher temperature. Okay, so you have to have a sort of fine tuning here. Okay, and so it is easy to deplete lithium in one star. It's difficult to deplete 100 stars, the lithium by the same amount in order to produce the lithium plateau. Okay, because you can imagine that if you have 150 stars, they have different rotational velocities, so different turbulence, and so on. So that's you have it's difficult to make all them lying on the same value. We also work about a model from the stellar physics and working on a Freeman sequence things. Okay, if you have, especially if you have overshooting, if you have the Freeman sequence phase, you have a lot of convection is much higher, and if you have overshooting, you can have a complete destruction of lithium. Okay. So we worked on that model with a complete lithium destruction in the Freeman sequence phase, and then accretion, because the star and star form, the accretion continues, okay? And at the end, the accretion can compensate, can refill with lithium the star, and then introducing a smaller plateau. So you start from the Big Bang value, primordial value, and you can reach a sort of plateau. But also in this case, you need some fine tuning, okay? This was our model. Well, of course, I cannot go into the details because you need 1 hour explanation. I think I want to go back now. Okay. So one important thing, if you want to avoid all the stellar complication, you can go to the interstellar medium. Okay? If you have lithium measured in interstellar medium, you can try. You have other problems, but you don't have diffusion, turbulence, problems like that. Okay. And actually, there was a measurement made by Clisso in towards a star Sandulet 143 in the small mathematical cloud. Okay, this is the only super unique lithium interstellar lithium extragalactic lithium interstellar detection made so far. Okay, so of course you have other problems because you have to correct for ionization in the cloud, and you have to correct for lithium depletion into dust. Okay, but he succeeded to do that. You can do that using potassium as a reference element. Okay, and he found in 2012 this element. Okay, which is consistent with the DDM. Okay, so the conclusion was that this measurement, interstellar measurement, was supported the original lithium as coming out of the DDM. Okay. And okay, I skipped this one. Sorry, I skipped this one, which is sort of defense of the.
Sorry, Dr. Molaro. If you try to find the lithium in a galaxy, let's say the extragalactic astronomy, we should observe the mergers than the normal galaxy, right? Because you are talking about this small Magellan cloud, so maybe we can find the lithium if you compare to directly the galaxy rather than to see the mergers, right? It is better way to find lithium. I don't know, we can find there, but it is better to find in the mergers as a galaxies.
Well, so far as I don't know what if I get your question. It is probably you say that it's better to find the interstellar extragalactic lithium
Yes.
in the mergers.
In the mergers, yeah.
Mergers of what? I mean,
The lithium 7, maybe.
Mergers of gas.
Merger of
Galaxies. Well,
Is it better way to find it? We can supposed to find, we will find there in the mergers.
well, you need a large column
hydrogen column banks.
I think, okay.
Okay,
So
so I don't think emerges, I don't think it's a good place where to find. I'm sorry, maybe we can discuss.
Okay,
later.
okay,
I don't think
just-
it's a good place.
I'm off topic, I'm not working on that.
You can have some plans. But anyway, okay, so what you see, one turning a low metallicity, these are all the lithium up down to -7. Eh? We have lithium detection in a giant. There is a second plateau for the giants, but what is I want to show you here that there are several lithium poor stars at very low metallicity, and this is because of low metallicity you start to see or to be dominated by the so-called carbon enhanced metal poor stars. I don't know if you've heard about. I mean, if you go at low metallicity, this range you have 30% of carbon enhanced metal poor stars, and then you have here you have total 100%. Okay, the most metal poor stars we know are carbon enhanced metal poor stars. Okay, and these are comes with two types, two flavors, where the so-called S and no S. The ones that have no need to capture elements, which are the yellow here, these are binaries, and they all have lithium depleted. Okay, so just to say that what's happening at low metallicity maybe could be understood. Okay, okay, this is the escape to the theory, and so actually you see that you have, even though you have low metallicity, you have a very constant value. These are all the gallium. You have 100, almost, well, not 1 million, but 100,000 stars here, and you see that. So this is another scale. You have to add 1.1. So that's 2.6. Okay, that's just the defense of the lithium of the speed plateau at low metallicity. But I want to come back to the interstellar lithium detection, okay, by Cristo, published in 2012. This is the original paper, and we repeated that because here the marginal detection of lithium-6, as you can see, the lithium-7, lithium-6 is plus or minus 3. So you can see that this is the lithium, also lithium is a doublet. Actually, there is an hyperfine structure, so you have 4 lines here. This is the lithium-6, okay? And it came out with a possible detection of lithium-6. So we repeated now these observations and come to the end, you know. We repeated this observation with espresso. Espresso is the new spectrum, but maybe you heard of high resolution, very stable, used for exoplanet. That we have a DLT that work with 1 DLT unit or 4 unit and have a resolution of 145,000. It's a very high resolution, very stable. And we observe intensively this same line of sight, and we get okay. This is the special observations. These are the original UVS observation, and here it's the lithium-6 presence. It's not there, so we rule out the lithium-6. But considering again the line, we also measure the metallicity in the cloud. Okay, the metallicity in the cloud using the zinc. You see, these are HST observations. Which are the zinc lines are here, the spectral noise. Zinc line, 1 zinc line here, and the second is here. Okay, so with the zinc is an alpha element. Sorry, is an iron picker, place iron, but is not depleted in the gas. Okay, so that's give you directly the metallicity, and we found with this metallicity of -1.8. For the cloud where lithium is observed. Okay, this is consistent, by the way, with the same stars, the stellar components studied by Michelletti et al. Where you see that showing the same radial velocity of the cloud, which is 132 kilometers per second, and you have sorry. You have the same metallicity, which is -1, -2, sorry, you cannot get the minus, but this is -1, -2. So you see, and the blue ones, okay, again, you see that are -1.8 Sorry, this is minus 1.5. This is minus 1.2, so it's exactly there. So this cloud has the same metallicity of the stars. And this lower value of Christoph assumed years ago. So the result is that if you take now a lower metallicity, you move the lithium interstellar extragalactic value from 2.7 to 2.2. Okay, so let's so to say the interstellar medium detection, the only one detection that we get coincide with the lithium measured in the hair. And so we get again a problem here. And this is my conclusion. I think that the revision of the second part, the revision of the interstellar value of both the standard and the SMC actually exacerbate, say that probably is not the solution of the cosmological little problem is not in the stars. That is what suggests new measurements. And I will submit this paper next week. Should have done this week, but I need to. And this is finished. Thank you. To detect extragalactic lithium, just to come back to your question, one of the best places are the DLA, which are these intergalactic galaxies with high hydrogen atom density.
Okay, maybe mergers can help to do some perturbation on stars that creates the interactions. So maybe now you are looking for the novas. Maybe the novas get help from the merging situation.
Galaxy interaction can play a role in another mechanism. If you have a spallation, enhanced spallation, actually, because if you have an interaction, probably you have a burst of cosmic ray burst rays, and so you may have more spallation, where you can have more lithium. And this model has been proposed, actually. I don't believe that, but there are several, efforts trying to explain the lithium problem, and this is also merger.
Any question? Okay, maybe I can ask some question. Well, on this summer appeal, I want to invite into my room to ask deeper questions about metallic line stars. I've seen some, like everybody, some lithium line to measure in stars. M stars show different range of lithium amounts, and also shows an abundance of heavier elements. These, I think, this may be correlated to birth of AM stars related to nova minerals. If the heavier elements are produced in nova also.
I think that are you belonging to the lithium collaboration or international collaboration for lithium in MSAT? No, okay. Because I think there is, then it's well known that M chemical peculiar stars have a lithium line, strong lithium lines. And it's been shown also that this lithium line is varying with the spots, because the magnetic have very strong magnetic spots of the stellar super star.
Not a magnetic.
That's M stars. Sorry, M stars. I'm confused. M stars. Okay, M stars. You mean very low mass stars? And but can you get the abundance out of that?
Yeah, actually, I got 3.2.
Okay, so that would be the what?
This is known as cosmic volume.
Yeah, that's because
we change cosmic volume from 3.2 to 2.2.
No, I mean, now you expect, the abundance that you expect now, in the younger star or whatever, is 3.3 now, okay? If it's not depleted, okay? In the young star, the deplete like the sun has been depleted with lithium. But the value, present value of lithium is 3.3. Okay, so if you have an M star, which is young or relatively young, you could have preserved the lithium.
I don't think so in my case.
You don't think so?
Yeah.
I mean, I know that regular.
I'll show my results, okay?
Okay. I mean, you know the work of Rafa and Regolo and Martin, Eduardo Martin, because, yeah, lithium can be used actually for the M stars in order to understand when if there is lithium depletion and not lithium depletion, and so you have a mass distinction.
So the third performance will.
Yeah, but I think that this, I mean, as I said at the beginning, there are a lot of lithium problems everywhere you look at. But I mean, I think this not solve the origin of, I mean, cannot make lithium, right? And galactic value. The M star.
I think you are working with Paolo one machine.
Yes.
Yeah. He is also working on K stars. Maybe he has idea.
Okay.
But I would like to invite the
That was my theory. Yes.
Thank you very much again, Paolo.
Say yes, yeah. I'm not understanding.